This is our presentation on long horizon model predictive control. Our initial goals for the project was we wanted to use a neural network to learn dynamics of a quadcopter to implement model predictive control with like a much longer horizon than usual. So this was based on a paper that came out by the Agile Robotics and Perception Lab, where they had neural networks to learn the dynamics of a quadcopter, and they were able to achieve significantly higher accuracy across much longer horizons than you could normally predict using just Newtonian dynamics. They did this with a couple different neural network architectures of like a multi-layer perceptron, long short-term memory, gated recurrent units, and like temporal convolutional networks. They proposed a few different architectures, like with different sort of encoder-decoder shapes, but the one they had the most success with was this decoupled architecture we'll explore in a little bit. But yeah, as you can see, they had very high accuracy across longer recursive predictions. The benefits of having this longer horizon length is that we have like less compounding error when we're integrating multiple states forward, and having longer horizons allows us to plan, like have much more complicated plans and aggressive flight paths and have higher accuracy across an aggressive flight path. And this is like necessary for like drone racing applications where you want to see much farther into the future and handle like obstacle constraints that are like much farther in the future. So we had a decoupled model architecture for this, where we had a sort of 14 dimension state where we had the velocity vector, the orientation, the angular velocity, and the previous control input. And we also maintained sort of the history of the like 10 previous states of this drone to pass into the model. So we'd be passing like a 10 by 14 for the velocity model, where we have like the 14 previous sort of states represented here. And then for the attitude model, it's the same thing, except passing it into a separate model. So we have two different models, one for the velocity controller and one for the attitude.
Yeah, so building upon that, we replaced the standard dynamics model inside MPC with the learned velocity and attitude models, which is trained on the history augmented state sequences. The state consists of position, velocity, quaternion, orientation, and angular velocity, which is going to be different than the 12D state of a regular quadcopter. But and these learned models predict the next velocity attitude from a sliding window of past states. We embed these models directly into the MPC optimization using L4-Casati to solve the nonlinear receding horizon problem that penalizes state, error, and control. And then we subject this to the learned dynamics and actuator constraints. However, when we deploy the learned models at MPC, we notice that closed loop performance degrades. And then the key issue is that there's a mismatch between the learned dynamics and the physical bandwidth of the quad rotor. As shown on the left on the frequency domain plot, the hover linearized system has extremely low control bandwidth with a -3 decimal cutoff in the order of 10 to the -2 hertz. And the learned model implicitly introduces faster latent dynamics through history augmentation, and MPC attempts to regulate these modes, even though the system cannot physically actuate them. So this results in an oscillatory behavior and solver infeasibility despite accurate open loop prediction.
Afterwards, we decided to compare this method's performance against an MPC controller that used a constrained LQR optimization. To build a dynamics model for the optimization constraints, we first linearized the translational Newtonian dynamics of a quad rotor in stable flight. We did this by using the small angle approximation to obtain a linear state space representation of the translational dynamics. Using the same method, we were also able to obtain the quad rotor's angular dynamics in the linear state space representation, which gave us the collective linear state space model for our optimization. From there, we would apply a mixer matrix to translate more dynamically intuitive control inputs into direct propeller control inputs. From there, we set the dynamics as constraints within the LQR optimization and applied it within a closed-loop MPC controller that would take the first set of control inputs in the optimal trajectory as its instantaneous control input.
And then these are our results.
Yeah, so going into our simulator, we simulated the system in MuJoCo. We modeled the drone dynamics using symmetric inertia tensor and realistic limitations on thrust and torque. We used the LQR controller with the receding horizon to actuate the thrust commands for each propeller, and we simulated this with some gates. So here are some of the simulation optimization plots we have. So for a given starting position as the green state, we tried to approach this target red state, which is assumed to be stable. And we plan the LQR gives us the best plan to get to that target. And finally, we also have some plots here of the different horizon lengths and steps and the effect of this on computation time. As we can see, 30 steps is a pretty good balance of trying to work towards our target state while keeping the computation time low. And this is what we thought would be like the optimal amount of steps through our experimentation. Finally, we can see by changing the cost values, the Q cost values, we can achieve varied results. So by penalizing the pitch and roll, we can see like drastically different outcomes, both in the orientation versus time as well as the trajectory we ultimately get. Yeah. Thank you.
Here are our results. We used a segmentation model to highlight the drone just to give some better clarity.